Bruce, welcome.
Thanks, Nick, and hopefully audio is all good, sounds that way. So, I'm here to tell you a little bit about my experience with Python in the classroom over the last 10 plus years, to give you a little bit of an idea as to where I am and who I come from beyond that little bio. I am a teacher primarily. I do a little bit of development still actively at school, writing mostly things for the school to deal with a lot of our internal processes that are grossly inefficient and use systems from the dark ages. And I've got an interest in curriculum, and for that reason put my hand up to be involved in the writing of the Australian curriculum and was lucky enough to be a part of that. So what I want to do before we get started is talk a little bit about the educational landscape as it is now. For teachers in schools, this is probably something you're very familiar with, although outside of your jurisdiction, there may be some things you're not completely on top of. But for other people in the room, this may give you a little bit of background and context that will help throughout the other sessions that are presented today. So I'll try to get through this nice and quick. Now, one of the problems that computing curriculums generally in Australia have faced is that often they're very, very dated. They're behind where the industry needs to be. They haven't been kept up to date for a number of reasons. Some of it has to do with the politics, some of it to do with teacher expertise and the lack of that that's present in schools. But the great thing is, things are changing, all right? There is an image problem that we're going to have to counter. The idea that curriculum in schools is very much about how to use the Office suite effectively or how to manipulate images in Photoshop. A lot of that is no longer the case, but a lot of parents and a lot of community members aren't completely up to date with the changes that are happening right now. So the digital technologies curriculum, which has been endorsed by all of the educational jurisdictions in Australia, is built on 5 key concepts. The one that underlies everything is abstraction. Abstraction and decomposition and related ideas. And on top of that, we've got the idea of data, properties of data, sources of data, how it's represented, interpreted, and analysed. We also have algorithms, the idea that definition, specification, design and implementation of solutions to problems is a really, really important part of learning in the digital technologies. Digital systems, such as the hardware and software that we use, networks and the internet, and finally, the role that people play on the way the systems are used and the impact systems have on our society. So that interactions and impact layer is something that is evident not just in the digital technologies curriculum area, but also in the other areas of the Australian curriculum as well. So as you can see, the digital technologies now is very, very different to what it may have been treated in schools generally across the country, and particularly in recent areas where ICT is generally seen as a tool for learning. And as a result, a lot of the curriculum around ICT has changed and has become a little bit more about using tools rather than creating with it. So where are we at with implementation? Well, I'm pleased to say that the ACT, where I'm from, as well as Victoria, where most of you are probably from, have decided and agreed to adopt the curriculum from 2016, and they're joined by South Australia and the Northern Territory in that. Queensland's not too far behind and has said that 2017 is going to be the year of adoption across the board. There they are. And in 2018, we expect to see almost everyone else join us. Now, New South Wales have recently released a shaping paper that sort of starts to define what the syllabus will look like down there, but being the largest jurisdiction in the Southern Hemisphere for education, it's no surprise things are going to probably take a little bit longer in New South Wales. But hopefully they won't be too far behind the rest of us and we'll be able to put another colour up there. So, my experience, okay, because I think it's important to understand where I'm coming from and to give you a sense of the kinds of challenges that teachers have faced and some of the solutions that we can all use and make in classrooms. First of all, I put this slide together. Originally it said teaching programming isn't easy, and then I revised it because I honestly believe that there are so many challenges involved in the profession of teaching that it's important that I emphasise that for anyone who's not teaching programming, you've still got a mountain of challenges that you've got to deal with. But I'm going to focus specifically on the programming side of things. All right, and I'm going to talk about some of the reasons I've found that it hasn't been an easy thing to do, but the fact that I believe it's getting much, much simpler. So some of the reasons for that is that generally programming when it's introduced to students is very, very unfamiliar. Most students have never seen programming before, when they're 15, 16, 17. It's generally not introduced in schools before that. So as a result, it's hard, right? When you compare it to the fact that if you do an English class or a history class when you're 16, you've been doing that for at least 10 to 12 years, all right? It's something that you at least understand that conceptually is not new. When you're throwing what is effectively another language at someone, all right, it's very, very difficult. But what I like to think is that that's going to change. In year 11 and 12, that's been a real problem for us in particular because it's high stakes at that point. And students are aiming to get the absolute highest score that they can as far as an ATAR is concerned. And what that means is that it's easier for them to drop out of the subject that's hard and do something that's easier, even if it's not stimulating or interesting, so that they maximise their ATAR for university entrance. And it's unfortunate, but that's the reality of the situation that I think is gradually changing. The other thing is, for those students who have had experience in IT in schools, it's been pretty rubbish. And as a result, they're not interested in doing it later on. If you have a really bad experience in an IT class in year 7, the last thing you're going to do is sign up for another 4 years from years 9 through to 12. The other thing is that a lot of parents and the community generally don't understand what the expectations of IT curricula are. So you're not going to, as a parent, say to your child, hey, get into it, it's really great, it's really exciting, if your memory of it was pretty dry, pretty average, if what you've heard from people who did it is pretty rubbish. And as a result, we actually need to address that issue as a profession and as a community. And I think there's a lot of work going on in that space. And in fact, even things like the National Innovation Science Agenda that's come out from the federal government is really pushing education to the forefront again. So hopefully the conversation that happens around this nationally is going to be really, really positive. So where did I start? Well, I graduated in 2005, started at a high school in the ACT, and there was one bit of programming in our curriculum. It was an internets and intranets unit, and it was JavaScript client-side make a quiz in the web browser, and it basically involved you taking the code that the teacher gave you and then changing the text in the questions and changing the answers, right? And then people were able to essentially do the same quiz. The answers were always in the same spot, unless you were smart enough as a kid to work out how the answer was determined. And, you know, you got an A for the assignment because people could answer all the questions right in the quiz. So, bit rubbish. I decided that that was all going to change. And so in the following year, we beefed it up a little bit. We still had students doing IT for the first time ever in year 9. But this time we added some server-side stuff to the course as well. We improved what we were expecting around the JavaScript side of things, and we introduced PHP as a server-side language. But what we found was students would just jump online, find code that did what they needed to do, and drop it into their websites. And the other thing that they did is if they couldn't find code that did exactly what they wanted to do, they just changed what they were doing so that it did what the code did anyway, right? So there's no real problem solving involved in that. It's basically a treasure hunt to find out how you can find bits and pieces that will fit together to do something that kind of resembles what you were planning to do in the first place. So I didn't like that, and we reviewed that, and we revised that, and we tried to prevent it, but it was very, very hard to make a change in terms of that attitude. So we wanted to expand our offerings. We were starting to get a little bit more interest in the courses because there was a little bit more to them than just, you know, making websites in Dreamweaver. So we introduced an object-oriented course, and the initial decision was to use Java. That was what the expertise at the school was, other than myself, and you know what? It was a bad idea. It appealed to students who were interested in it, who were keen to sort of do the additional research to understand what was going on. But a lot of students saw how much code was involved to print a simple message on the screen, and all of these extra words and things that didn't even seem to be necessary, and simply switched off. And it was really, really hard for us to maintain interest, particularly with the students who were kind of doing it because they thought they might be interested, but didn't actually know what was involved in actually programming. So this all had to change. And in 2009, we decided that we were going to adopt Python and use the NCSS challenge put together by the University of Sydney as our primary means of introducing programming. And it worked really, really well. In fact, it's probably been the most successful transition I've ever done in terms of the classroom. We were able to do it at year 8, 9 and 10 level. The year 8 struggled initially. The challenge only had one level early on and it was probably pitched a little bit too high for those students. But over time, the NCSS challenge introduced additional streams. There was additional scaffolding added to the notes, to the questions, and as a result, we were able to use the NCSS challenge exclusively for all of our introductory programming courses, regardless of the year level students we're in. And that used Python, which was great. So we shared that success with every other school in the ACT through the Professional Association for Teachers down there. And as a result, we got more interest. Has it been adopted generally across all schools in the ACT? I wouldn't go that far to say yes. But we do have more schools now who are at least picking up Python as a language because they've been impressed with the ease with which students learn it. They're not always using the NCSS challenge. There are a number of reasons why they're sort of choosing other tools, but essentially that increased visibility of Python in schools in the ACT has made a big difference to the quality of programming and computer science education down there. So at Gungahlin College, which is the school that I'm at, Python is now our primary language. We use it for everything with the exception of our embedded systems unit. So I'm really keen to see what's going on in the MicroPython space a bit later on today. But we've got the highest IT enrolments for any secondary college in the ACT across all private and public sectors. So we get 170 students in year 11 and 12 alone, and we've got a school of about 1,000 year 11 and 12 students. So yeah, that's not bad. If a fifth of the population is enrolled in an IT course, we must be doing something right. Okay, we're really excited about that. We're looking to grow it further. It also means that we can maintain 2 full-time plus an executive teacher just for IT teaching, which is great because it means that we can attract the people who are keen and who have the knowledge and skills they need to be able to deliver on what is a very demanding curriculum. These are the reasons we essentially went with Python in the end, and I think they're reasons that a lot of people in here would be familiar with, so I'm not going to spend a whole lot of time on this slide other than to say that the one that's probably been the biggest, that's had the biggest impact for us is the friendliness of the language. The fact that it's got a really sort of simple syntax and it does have a lot of similarities with pseudocode that other students may have seen before through their other IT courses. And that's particularly important for us in a secondary college where we only see students for 2 years. They come to us from year 10 from a number of different schools in the area. We don't know what their prior experience has been, so we have to start at a point where we've got students that have literally done nothing before and other students who have completed the advanced stream of the NCSS challenge for the past couple of years. And we need to challenge students in both of those categories and everywhere in between. So the fact that it's friendly and easy means that we can onboard beginners very, very quickly. And those that have experience in programming, even if it's not Python, can make the transition to a new language very, very quickly and then can actually spend their time in the classroom investigating more interesting and engaging things. But I have to say, it's not, perfect. There are obstacles and challenges that we're still facing. And the 3 big ones for us have been around, first of all, graphics and games. If students want to create something from scratch, it's not as easy to do in Python when compared to other languages. That doesn't mean there aren't platforms out there, and in fact we use Pygame quite extensively to do that, but it's not as easy as it might be for them to say fire up Unity or Unreal Engine and get stuck into games through storyboarding or something like that. So I guess I just wanted to sort of emphasise that that is still a challenge that we're continuing to work through. Integrating with peripherals or making use of external peripherals that aren't keyboard and mouse can be a challenge depending on the nature of it. Sometimes it is, sometimes it's not. And so students are sort of reluctant if it's not something that they can be confident is just going to work for them, like most of the other things that they're dealing with in the language. And bundling applications up so that they can be used on any machine anywhere else is also a real challenge for us. And again, there are packages that do that, but the effectiveness with which they do it is always a challenge, and students like to sort of use these sort of obscure modules and things that they find online that kind of do what they want to do, and they get really familiar with that, and then they forget to tell you when they submit their assignment that you need to go and install it, right? And so you have to spend the first little bit of time finding out which modules you need to get and putting them on. So, I mean, they're not big things, but what we find is that experience solves a lot of them. Students in Year 12 can cope with this quite comfortably. The students in Year 11 earlier on in the course do struggle a little bit. So what have I learned from all of this, right? That's ultimately what I think the most important thing that I need to address through the talk today. So There are 5 points that I want to highlight, and the first is this: keep things as painless as possible for students. All right? Now, how do you do that? You teach the fundamentals explicitly, and you make sure that students understand what's going on. One big trap with Python is that it's easy to do lots of things without kind of really understanding exactly what you're doing, right? Because things can be done pretty easily. But when students are trying to manipulate something inside an array or a list, and they decide to use a for loop, and they think they're writing over the top of their variable, but then it doesn't change, right? Understanding what is actually going on makes a big difference, not just at that point in terms of their learning, but also in terms of any future learning and projects and programs that they're going to work on later on, because they know what to expect and they know what kinds of solutions are not going to work. So there are a few tools we use to do that. I've mentioned the NCSS Challenge, and Grok Learning subscriptions are standard for every student that comes into our school. We sign them up, we pay for it, it's part of their school fees, and we're a government school, so fees are optional for us, but we build it into our budget as one of our few IT expenses. We also use the Interactive Python website. There's an online textbook, the How to Think Like a Computer Scientist textbook, that a lot of people are probably familiar with. The entire thing is online and has a whole heap of interactive projects and things that you can work through. So we'll often direct students to activities in there to support the stuff that they're doing on the Grok platform. In addition to that, Code Academy provides some really easy sort of drill and practice additional support for students who maybe get through the stuff that we've got access to through the other platforms very, very quickly. So it's just a way that we can sort of direct students somewhere else for a little bit more kind of practice and drill. Coursera's great. We rely on the sort of intro-level university courses to give students a grounding in ideas and concepts that they might use in their projects in Year 12. So we do rely heavily on that for that. And in fact, there's an entire course on there that covers a lot of the principles of computational and algorithmic thinking that we rely on quite heavily. And Pygame we use for a lot of our graphics and Pygame stuff and game-related stuff. So yeah. The great thing about this is that the majority of them are very, very easily accessible. Grok is effectively free for our students. So as far as students are concerned, all of this is free to them and they can access it. And the quality of resources generally is really, really good. So once you've taught them the fundamentals, the thing to emphasize with any project that you set is the thinking, right? Because they learn very quickly that they can code, and they can code pretty easily in Python, right? But when you give them a new task, if the first thing they do is sit down and try to bash out an answer, they're going to create a rubbish answer, right? And they're going to have to go back and rewrite their code and rewrite their code and rewrite their code. And then they complain that we haven't given them enough time, the deadlines are too tight, and it goes from there. I tell them they're wrong, of course, because I set the task and I know how much time it should take you. So what we do is we make sure we really emphasize that whole thinking process. And the way we do that at Go in college is we've given them a kind of framework with which to think about a problem. And it's modeled on a design thinking framework, which sort of coincides nicely with the Australian curriculum and the expectation that the technologies learning area is sort of built around 3 types of thinking: systems thinking, design thinking, and computational thinking. And you can see there that we emphasize a lot of sort of working together, some collaboration, some active kind of group engagement with any of the activities that we do. That's a fairly sort of standard introductory sort of lesson when we're introducing a new project or concept that we use. I like the fact that we don't have a lot of walls, we don't have a focal point in our teaching space, but I'll come back to the environment a little bit later on. So, relevance is another important factor, right? When you're teaching fundamentals, it's fine to sort of focus on the mechanics and make sure the understanding of what's going on under the hood is clear to students. But when you're giving them a project, it's not enough to say, oh, you're just going to write, 100 while loops to make sure you understand how a while loop works, right? That's the old sort of maths textbook drill and practice idea. And we know how effective that's been with engaging students in mathematics who aren't really interested in it, right? So one of the things that we really emphasize is that the projects that students are working on have to be relevant. They have to be interesting problems for students. And that's not going to be consistent and common for all students. So you have to be flexible in terms of how we set these things up. So these are some examples of student projects that have been put together. I actually have a session on Sunday where I'm going to showcase a lot of these. So I'm not going to spend a lot of time on them now, but games in Pygame are common, data visualization for a data set that they choose. This is a pathfinding tool that was built on the basis of sort of uploaded maps that you create, so it's not predefined in any way. This is a simulation for a mechatronics project that a couple of students are launching. This is how they're going to determine where they're going to be recovering the payload from their high altitude balloon that they're launching is. This is a predictive text and parity text generator that a student built using Markov chains. This one here is a text summarization tool that uses TF-IDF and k-means clustering to work out what the most important aspects of a published article are. And this is a handwriting recognition tool, which uses a trained neural network to determine exactly what's going on. And I mean, this wasn't exactly accurate in terms of but he trained it with his handwriting, and my handwriting on a touchpad is clearly far worse than his is, right? So that's just an example of the kinds of projects they're working. They're all interesting for the students involved, right? And we haven't been too prescriptive in terms of what they need to be doing. The collaboration is key, right? Make it social. It's particularly engaging for girls this way, right? One of the real challenges that a lot of teachers have with engaging girls in programming is that it can be a little bit isolationist and the classroom can be dominated by guys. But if you give them opportunities to collaborate, if you can give them opportunities to lead that discussion, to make it very, very clear to others in the group that they are just as knowledgeable, if not more so, than others, you can help counter some of the stigma associated with that. So we do that with our environment. This is our new teaching space. The one you saw last on the other slide was last year's space. As you can see, with bench seating, some smaller seating, we've got a bench up the top. The tables at the back have a whiteboard surface that we use for students to sort of collaborate on the whiteboard space. The TVs are all open access, so it's not restricted to teachers, and students use that for collaborative discussion and code. Just some shots of students working together there. The other thing that we've also done is we've provided plenty of space around the classroom for them to do their planning and brainstorming as well. So that's some of the brainstorming work the students working on the simulation project we're doing. So the fact that they've got all of that access means that they're not restricted to a single space in their classroom, and they can get out there and they can use the environment the best way for the particular aspect of the problem they're working on. And finally, keep the projects open-ended. Right? And that's probably a little bit obvious through the variation that I've provided in some of those other student examples. But even for the simpler tasks that we set for students at an introductory stage of the course, we follow a standard framework that ensures that there's something in it for everyone and that there is no sort of endpoint that you hit, 3 days in if you're all over it. That means that you're kind of done and you're disengaged for the rest of the time. So we get them to document any of the code that we provide to them as a means of making sure they understand what's going on already. Then the goal is to improve the existing code, then expand it, and then redefine aspects of it that you want to change. All right? And the good thing about this is everyone can get through the first two parts, even if some require quite a bit of teacher support to do it. And the bottom is where that open, sort of unstructured, free-for-all learning happens. And that's a really, really great model to use if you're looking at a way of sort of thinking about how you might structure tasks for IT projects. So I asked a couple of my students, why did you like learning Python? Right? And these were the responses I got from them. Now, Kat came to us in the middle of year 11. Right? She's the one who wrote the parity text generator and the text prediction software. She wrote that having done programming for 9 months. Right? So this is a student who came to us very, very late, but was sort of really enthused by it, and she liked the fact that she could just pick it up and run with it very, very quickly. All right? I asked her, she's been learning Haskell at university this semester, and one of the things that she said is there's a whole heap of stuff. I mean, first of all, it's a completely different way of thinking about programming, right? So there's a challenge there already. But when you compare it to how easy it was to pick up something like Python, right? There's a whole heap of stuff going on that you sort of don't need to understand to be able to do things, but if you understand, it makes a huge when she was using Python. She felt like everything that she learned was very easy to understand, and it was pretty sort of upfront and obvious. Damon, another one of our students, he started programming in year 8, and he found that the fact that the code kind of gets out of the way because the syntax is so easy meant that all of the learning that he actually did was around the problem solving, right? Thinking about how you're going to come up with your solution. And so that set him up really, really well for future projects that he built. And he was the one who built the pathfinding tool for custom maps. Right? And they use computer vision to scan the map that you upload to work out where the various nodes are, and then they use A* for pathfinding. So this is the too long, didn't read version of my presentation, right? The 5 key things that I think you need to keep in mind when you're going to teach Python successfully. Emphasize the fundamentals, right? Don't assume them, teach them, be explicit about it. Explicit teaching has a role, and making sure that the fundamentals are understood is a really important part of that. Emphasize the thinking, because well-designed code is good. I mean, it's good for many, many reasons, right? But it means that it's reusable, and it means that when it comes time for you to solve different problems, you're going to be well-grounded. Keep things interesting, right? Because if it's not interesting, you're going to lose them. And make sure that that's designed in your tasks. Encourage rivalry, but make it friendly. If you can get rid of any sort of antagonistic kind of competition in your classroom and get everyone working towards the same goal, you'll actually get better results across the board. And students need to understand that. Even in a competitive environment, that friendly rivalry makes a huge difference. So collaboration is key to that. And finally, don't restrict creativity, right? Programming is as much as an art as it is a tool to solving problems, and it's important that students can see that really, really early on. So that's it from me. I'm happy to take questions in the last time that I've got. Hopefully you enjoyed it.
Thank you very much. Thank you very much, Bruce. And yes, we do have time for questions, so put your hand up and I'll bring the mic.
Thanks, Bruce. That was awesome. 2 questions, 1, 2 or 3, and 2 OS/BYOD/ problem.
Okay, so we're a BYOD school. Yep. I've worked in the prior school we weren't, and we just pushed things out on every machine that we had. At the time, we went with Python 2 for Pygame support, but since then, Python 3 it's no longer an issue. Because we're BYOD, I'm not too restrictive with Python versions. Also, when students are working on different projects, they will need like modules that are only written for Python 2 and things like that. So the fact that fundamentally, for most of the work they do, there's very little difference. We sort of point out the fact that the print statement's different and the input statement works a bit different, and that basically covers most of it for the introduction. So they learn Python 3, but often the switch to Python 2 is necessary for some projects. And the fact that there's no significant complication with installation means it's ideal for both BYOD and a lab environment. Yeah. Who raised the mic? Here?
Yes, just in terms of the curriculum, from what I saw, a lot of it builds on the sorts of conceptual curriculum that you might have in say, mathematics. So could you comment briefly on what overlap there is with mathematics and how you deal with it at a teacher-to-teacher level?
Sure. So I think there are going to be a couple of talks later on, in fact, about Python and maths. So I'm going to leave aspects of that to those because I don't want to take anything away. But one of the advantages of the digital technologies curriculum being written last is that it was able to be written on the basis of a sequenced mathematics curriculum. So you'll often see that there are concepts being explored in mathematics that fit very, very nicely into where you are sequentially through the digital technologies curriculum. Ideally, I think the concept of teaching in a subject area needs to be thrown away completely, right? We don't learn in individual subjects. We never have and we never will, and we don't work in that space either. So I think what we need to be doing is talking to our maths teacher colleagues, and we do this a lot at the college. We have students, as an example, doing a lot of probability and statistics when they're in Year 11 doing their methods course, and we use that when we start introducing things such as artificial intelligence. So we'll actually have a look at things like the Monte Carlo method and how the probability plays into that, and what we've actually found is that students who do our projects have a much better understanding than the students who have done it only in mathematics, and often that's because they've been given an environment in which it actually has meaning. So.
Thanks for that talk. So, very enlightening. My question revolves around your first point regarding fundamentals. So by fundamentals, do you mean fundamentals of the actual language? Or do the fundamentals change depending on the project? So for example, you just mentioned Markov chains. So do you introduce different skill set for that, for them to be able to handle it?
Yeah, so the focus here was specifically on the fundamentals of the language, so that when you're using the language later on, you understand it. When it comes time for students to do their projects, and one of the things I'll sort of discuss on my Sunday presentation is a little bit about where that fits inside the curriculum in terms of these concepts you're talking about. But what we do is we give students the opportunity to identify the concepts that are going to be most relevant to their interest area. So when she came to us and said, I want to do text prediction, one of the tools that we identified at that point was Markov chains. We directed her to the appropriate information so that she could go and find out about it herself. We actually paired her up with practicing software engineer at Atlassian who was able to help her out and talk to her about that as well to give her that additional support. And on that basis, she was able to take that understanding and her knowledge of Python and build what was a pretty cool application. Now, I should emphasise all of those projects were done in 3 weeks. So it's not like we give them months and months to work on these things either, right? So when it comes to that, it's impossible to teach everything to everyone, right? So what I've done over the last sort of few years is identify appropriate resources for emphasising those fundamentals, and then I direct students to what is appropriate for their particular project.
What others?
For the language fundamentals, really it's just the underlying control structures, understanding how when you store something in a variable, it's actually dealt with throughout the program. The concept of scope is important. When you're introducing OO, what an object is, how it's a representation of data and all of those kinds of things. It's just emphasising that you're not just learning a statement, understanding what that statement is doing so that you understand how that data is being manipulated and moved around in the greater program. That kind of stuff, yeah.
And this will be our last question.
I love your focus on real problems. I'm just curious to know, you said you had, I think, electives prior to year 11 and 12. Are they?
We don't, but our other schools do, yeah.
Okay, so you just have kids coming into year 12. What kind of skill differential do you have?
It's massive. It's huge, right?
Okay.
So, as I said, Kat came in second half of year 11 with no knowledge, and Damon had been programming since year 8. What we do is, for the students who have that background knowledge, it's still in their interest to do the intro unit, right? Because they're going to get a massively high score, which is going to help with their ATAR. But what we do is we ensure that as they're working through the problems, we won't just introduce the while structure and let them sort of work through it and understand what's going on, because they already know that, right? They just need to know the new syntax. So what we'll do is we'll actually give them interesting challenges and ask them to only solve it with that type of solution, right? And that's where we can actually start introducing the idea of things like recursion pretty early on with those kids rather than leaving it to the normal spot in the sequence. So that's how we address that.
Thank you very much, Bruce.
All right.
And